Okay, fantastic. Welcome, friends. Welcome, everybody. Today we have our fifth lecture. I'm about to share a screen, but I just wanted to show you, this is a cuatro, which in Spanish means four. And this is an instrument from my country, Venezuela. I play it not very well, and people with perfect pitch can tell that this is not completely in tune. But we're going to be using this at the end of the lecture whenever we start talking about Fourier transforms. So that's why the cuatro is in there. Okay, let me share my screen. Okay. Aha. So this is lecture 5, not lecture 4. Yep. So, welcome, friends. Let me share. Why is this so annoying all the time? My video button. No meeting controls. Okay. So, today we have our fifth and final lecture for the math part. Starting next week, we're going to start with classical mechanics on Mondays and quantum mechanics on Wednesday. Quick reminder that we have the resources for all that we're doing in this Google Drive folder. I have successfully uploaded every recording of every lecture that we have had, and I'm very happy with the outcome. Kyle and I recorded a video yesterday. It's like 10 minutes. It's going on how to use the GitHub forking and pushing and pulling repository actions. That is what they need to follow if you want to add your playgrounds to the playground area. For those of you that are starting to join us, we're calling homeworks playgrounds because they're not homeworks, because you're not grading anything and you're not obliged to do any of those things, but rather you can play with it. So if you want to submit your things and you have never done that and don't know how to do it through GitHub, watch the new video recording that I uploaded with Kyle. This is a summary. Let me, where do I put this? Here. This is a summary from last class. On Monday, I think we had a lot of fun. We play with the rope to describe the easy states or eigenstates or normal modes or eigenfunctions, however you want to call them. In my eyes, these are the states of your system that makes your operators or whatever else you're playing with look trivial. Cases of matrices, they're eigenvectors. Those are the vectors that the matrix is just multiplying by a number. In cases of differential equations, might be a bit complicated, but it's basically the same. And we played with the eigenstates of the physical rope by letting it evolve as a function of time. And we played with some animations in where we show that indeed you can decompose this function, which is the rope, describing the rope at every location x and at every time t. You can decompose it as a linear superposition of the normal modes of the rope. And to find these coefficients of this expansion, what you need to do is use projections, which in the case of functions are integrals, and you're going to be able to find those coefficients. And this, in my mind's eye, is completely equivalent. Hello, is completely equivalent to projecting with a lantern your function f at the initial condition into all the different vectors that are the other functions. So it's exactly the same thing that we did 2 lectures ago on the floor with the vector, but in something that might have 300 dimensions, 500 dimensions, or infinite dimensions, depending on how detailed you want to go. The second part of the class, and we're going to discuss a bit more about linear algebra in this class as well, we discussed linear algebra as linear operations on vectors, on finite dimensional spaces. And the analogy that we discussed was thinking that vectors are ingredients and matrices are operators, operations that you can do on those ingredients. In here, I have the example of the cutting or chopping operation and the freezing operation. And then what you're doing in linear algebra is just acting on your ingredients in different orders by the different operators and just finding out what you get, basically. And at the end of the day, that is such that you can maybe prepare a cake for somebody. In the case of math, so that you can describe physical systems. Important to remember, some steps will not commute. It's not the same to chop water and then freeze it than to freeze it and then chop it. You're going to obtain 2 different things depending on the order that you put those things in there. So that is a nice visual reminder of the non-commutability of linear operations. And this is a picture of the matrix that we were playing with, that we're going to come back to it in a second. in where the two eigenvectors of this matrix is the one in red and the one in blue, and the eigenvalues are just 3 and 1. Any questions so far from this summary? Very well. The playground for last week was to double check the Jupyter notebook that has all the resources for linear algebra. If you're unsure on how to even multiply matrices, which is completely fine, there is an entire notebook that will guide you through that process and getting the eigenvalues and eigenvectors. I also wanted you to try to make a vector plot like the one that is on the Wolfram Mathematicas webpage on the action of this matrix on vectors themselves. And then the other two things was to repeat a similar thing on 3D and to add a list of miscellaneous topics that you wanted to see for today's lecture. I think only one person added something, and I was already going to cover it, so we're good on that side. I want to say this, and I will put this somewhere in the Drive link. Since we're stopping math completely today, and we're going to start with classical and quantum, I will be more than happy to record short videos on specific topics. If you tell me, Pablo, for example, I don't think I'm going to be able to talk about variational calculus today or delta functions and Heaviside functions. If that is something that you would like to know, you just let me know, and I record a 10-minute video on that topic, and I upload it to the YouTube channel, and then you can access it later, and it will be useful for your education. So that is an option that we can do. That's what I want to remind us. In this class, we can now go over those topics in depth. Before I put the menu for today, anybody was able to play with this playground? Anybody has any comments about it? As I said before, it's not an imposition. Maya, you did it. Tell us all about it. Were you able to upload this to the GitHub, which I haven't checked? And I will start checking it, I promise. I'm sorry. You have. Fantastic. Any comment that you want to add on that? If not, I will look at it. You added a PR. What is a PR? Pull request. Okay, and I haven't accepted that pull request. I will do that later today. Thank you very much for playing with the playground. Once I do that, I will show it off on Monday, and we can discuss it in more details. Thank you. I will be more careful for the next lectures to check the GitHub before the lecture. But very, very good. Any other comments? Okie dokie. So today we have a special class because I want to finish some discussions in terms of math. Let me close the door so we don't have much interference. So today we have a special class because I want to finish some details about the matrix part, but then is miscellaneous topics that, of course, it is impossible to cover all of the things that are on the board right now in detail. But as usual, I want to give you intuitions on how to visualize these things. And later on, we can discuss them in more details shall questions arise. But today, we're going to go over some more linear algebra. And then I'm going to go all over vector calculus, complex numbers, the residue theorem, Fourier transforms. And most likely, I will not end up in time to talk about Heaviside and delta functions, but I will make an extra video recording about that. So with that menu in mind, let me switch to my tablet. So let's start with just a tiny recap of last time eigenvalues and eigenvectors, because I want to talk about change of basis. That is what I want to say. Yes, okay. So you remember the matrix that we were playing with was this matrix. And if we made a plot, a vector plot of what this matrix is doing, it has two eigenvectors. One eigenvector is here. I'm going to call it phi1. Another eigenvector is here. I'm going to call it phi2. And it has eigenvalues lambda 1 equals 3 and lambda 2 equals 1. And these eigenvectors and eigenvalues are important because the action of this matrix M on phi1 is equal to 3 times phi1. The action of this matrix M, put arrows, on phi2 is equal to 1 times phi 2. And these are very special vectors. Most vectors are, any other vector that is not this one, or a multiple of these vectors, are the action of the matrix on the vector is going to be much more complicated. So these are very important vectors to understand the action of the matrix everywhere. But also, if I were to tell you, suppose that I have a new vector v, let's not put it in green, put it in pink. I have a new vector v that is sitting in here, is not phi 1, but is close to phi. According to your intuition, what do you think will happen to this vector whenever I act with the matrix on it? Any ideas? Sorry? As a first approximation, what is going to happen is going to extend its length by 3 times because it's very close to the vector phi 1. Everybody sees that? You could refine that a bit more because you could say, well, if I were to project this vector in the phi 1 direction and another component in the phi 2 direction, you see what I'm doing? I'm putting a lantern here and another one in here to look at the shadow of this vector onto these two axes. If you do that, you see that the blue one, the blue projection, is going to get multiplied by 3, as you were saying, but then the orange projection, nothing is going to happen to it. It's just going to be multiplied by 1. So if somehow I was able to express my vector v as some coefficient a times phi 1 plus some coefficient b times phi 2, I will be able to understand what happens to this vector through the action of the matrix on the two eigenvectors. Basically, what I'm trying to say is that if I have a vector v that is written as x, y, where this means, do we call this, well, this is x in the 1, 0 direction plus y in the 0, 1 direction, right? And these are my canonical vectors. That is the original basis that I was in. If I'm able to change my basis and express this vector as a linear combination of these two, I'm going to be in a much better position to understand what is happening to that vector. Any ideas on how to obtain these coefficients a and b?
Using dot product?
Using dot product.
Projection.
Projection, yeah, exactly. Yes. So if I were to say, let me grab my vector v, this. So my vector v, I said that is x and y. If I do v projected on phi 1, which is the same in Dirac notation as v phi 1, this is going to give me my number a, if phi 1 was properly normalized. And that is something that I'm assuming that is going to happen. The same is if I were to project my vector v, we usually do this in the opposite. That's okay. In my vector phi 2, this is going to give me do it right because these videos are going to stay forever and I don't want to speed this up. V 1 phi 2. So for example, let's say that the vector v is equal to the vector 1, 2. So to write this as a linear combination of my two vectors, what I need to do is say, I first need to make sure that phi 1 and phi 2 are normalized. So if you remember correctly, if I remember correctly, sorry, this vector was 1, 1, and we're going to divide by the square root of 2 such that it is normalized. My vector phi 2 was 1 minus 1. Yeah, put it minus 1, 1, doesn't matter, times 1 over square root of 2. So then, for this specific example, I multiply, so it's 1, 1 with the square root of 2 times the vector we said 1, 2. And this is equal to 1 over the square root of 2. 1 times 1 is 1, plus 1 times 2 is 2. So this is equal to 3 over square root of 2. And then, so this is A. What was the color that I used for A? So this is A. And then for the other projection, 1 over square root of 2 minus 1, 1 1, 2, equal to 1 over the square root of 2 of minus 1 plus 2. So this is equal to 1 over the square root of 2. And this is going to be equal to b. So let me put it in color. So this is telling me that my vector v, and this is extremely important. When you write your vector v in this notation, this means 1 times x hat. X hat is a vector 1, 0, plus, in that basis, plus 2 times y hat. But I can also write v, and it's the same v, as 3 over the square root of 2 times phi 1 plus 1 over the square root of 2 times phi 2. And I'm talking about the same vector. If this confuses you, and to me, seeing this notation confused me, because in this notation, this is a vector 1, 2. But if I'm talking about these bases, in these different bases, this vector is going to be the vector 3 over the square root of 2 and 1 over the square root of 2. Because these two objects are written in a different basis. If it helps you, the analogy that I tell myself whenever I get confused with this is literally think that this is the same book written in two different languages. I can have the book of Don Quixote de la Mancha, the crazy guy that was fighting against the windmill things and all the adventures that he had. I could have a copy of Don Quixote in Spanish, so that would be the canonical language because that's where Don Quixote was written. So in here, this is Spanish. But I could have a translation in, I don't know, French. And it's the same book. But if you open the book and you read the characters are different. It will not open in the same way. En algún lugar de la Mancha de cuyo nombre no quiero acordarme, blah, blah, blah. That's how Don Quixote starts in Spanish. If you open the book in French, it will say something else. I don't speak French, so I don't know what it will say. But the characters are going to be different. The book is the same. Does that make sense? So it's extremely important that in your life, whenever you see this, and if somebody says, my vector v is equal to 1, 2, there has to be a language attached to 1, 2. That language is what is going to tell you how to interpret this vector. If I am in the canonical basis in where 1, 2 means 1 times x hat plus 2 times y hat, that is a specific vector. But if attached to this notation, I am telling you, hey, no, I am writing this in French, then these numbers are going to be multiplying the different bases, and in this case, it's going to be phi 1 and phi 2. And depending, and this is very important, depending on the language that you use, some things are going to be easier than others. I don't have a good example. Well, I guess if you go to a French restaurant in France and you start ordering in Spanish, they might not be very happy with you. So saying the same thing in a different language might be easier or harder depending on the circumstances. But that's basically what a change of basis means. Now, the final thing that I want to say about this, because I want to move to something else, you can write something that is called a change of basis matrix. It's a linear transformation that is going to, it's a matrix basically, matrix M. How do we put it? What is the usual notation for changes of basis matrices? I'm going to put MC for the matrix that changes your basis. This is not the standard notation. I just forgot what people usually do. I can write this change of basis in such a way that whenever I have my matrix and I multiply it by a vector v, in this case, it's going to give me back my vector v, but this is in Spanish and this is in French. This is basically the matrix whose operation is to translate things between languages. Yes? Such that I don't have to come and do this entire nonsense with the projection every time by hand. I don't have to rationalize what I'm doing in that case. How do you write this matrix? It's very easy. What I usually do with these things, I ask myself, okay, can I figure out to where the matrix change of basis will send the vector 1, 0? This is going to translate the vector 1, 0 to some new vector in the new basis. And then the basis, the matrix MC is going to also translate the vector 0, 1 to another element. I need to figure this out. I still don't know what these two are. But once you figure those out, basically that is going to be how your matrix looks. Why? Because suppose for a second that this sends, let me assume that MC, the matrix MC, that is a 2 by 2 matrix, acting on the vector 1, 0. Actually, let's figure this one. That shouldn't be hard. Basically, is how can I write the vector 1, 0 as a linear combination of these two vectors? What do? I just do the projection on the vector 1, 0 on my vectors. This is going to be 1, 1. This is equal to 1 over the square root of 2 of 1. And then if I write the vector minus 1, 1, 1, 0, this is equal to 1 over the square root of 2 minus 1. So that means that the vector 1, 0 in Spanish, which is equal to x hat, according to this is going to be equal to 1 over the square root of 2 times phi 1 plus 1 over the square root of 2, not with a plus, but with a minus, times phi 2. And you can convince yourself that this is true if you substitute the definitions for phi 1 and phi 2, you put them back here, you end up obtaining the vector x hat, which is 1, 0, which is the vector that is pointing to the right in Spanish. Why I'm saying all of this? Because now you see that this matrix MC applied to the vector 1, 0 needs to give me the vector that is 1 over the square root of 2, 1 minus 1. Everybody follow that? Yes? Any questions? Because I'm about to say something and then we're going to jump to a different topic. So if this was not clear enough, this is a moment to interrupt. I also want to tell everybody that is present in here that I fully expect these videos to be enjoyed by generations of people in the future to come. If there is something that I'm saying that is not clear, it's clear in my mind, but it's not really clear, and you're having questions, you being very brave and asking the question is going to help millions of viewers that we're going to have through the generation. So don't only do it for you, do it for everybody else that is watching at home or somewhere else right now. Is this clear? I see a couple of enthusiastic yeses, and I see some people that seem to be on the verge of asking. Some folks, is there any question with what I just did? Please.
I have one quick thing. So up above, you drew what the new vectors were for the basis that we're in. You would need to solve the eigenvalue problem to get those, right?
Yes, I'm assuming that I already solved that.
Right, so that's the first step in this whole...
That is the first step in this whole endeavor, yes.
Okay.
But we solved that last class, so I assume, okay, I already know the eigenvectors, and now I already know the new language, French, but I now need a translation operation that takes me from Spanish to French.
Right, okay.
Very good question. Any questions from Zoom? Okay, so here's the magic. My question to you, friends. If this is true, that the vector 1, 0 needs to be sent to 1 over square root of 2, 1 minus 1, can you tell me anything about the matrix that is on the left? Can you tell me anything about this object? There is the microphone on.
The first column is exactly the 2.
Very good. So the first column of this matrix should be 1 over the square root of 2 and minus 1 over the square root of 2. Why? Because the way that you multiply matrices, when you multiply these two things together, you're going to grab this vector. Let me do that. You're going to grab this vector, put it like this, and do this. And that is going to give you this thing. And then you put it here, and that is going to give you, oops. And that is going to give you this thing. So basically, that column tells you where the first vector of your basis get maps to. How do you figure out the second column? What will you do?
Other vector.
Microphone.
Consider the other y.
You apply it to the second vector. That is the beauty of linear transformations. That's why we are so obsessed with linear algebra. In linear operations, if I know what happens to the basis, I know what happens to everybody. because everybody can be written as a linear superposition of the bases. It's a linear transformation, so the transformation applied to you, it's the same as the linear superposition of the transformations applied to each element of your bases. If that sounded a bit complicated, let me know afterwards and we can try to disentangle. But that is, in this case, how you end up building the change of basis matrix. What is going to be the other numbers? Let's figure out that quickly. So if I want to write the vector 0, 1, which is y hat, as a linear superposition of these two things, what changes? What changes is so what changes is that I have 0, 1, 0, 1, and in here I got the exact same thing, 1, and in here I have 1. Okay, so small corner in here. This is equal to 1 over the square root of 2 phi 1 plus 1 over the square root of 2 phi 2. So that means that whatever my matrix MC, which we already know is 1 over the square root of 2 minus 1 over the square root of 2, when it gets multiplied by the vector 0, 1, this should be equal to, how much did I say? To 1 over the square root of 2 times 1, 1. So that means that this matrix has in here 1 over the square root of 2, 1 over the square root of 2. And that's it. I got my change of basis matrix. So if in the future, I come and I tell you, I have a new vector, I don't know, let's call it W. Remember that we had the vector, I think 2, 1 is the vector that I said. And I come with a vector minus 17, 3.5 in the canonical basis, and I want to write this vector in the new basis. The only thing that I need to do is multiply this vector by the change of basis matrix, and I'm done. That is how I'm going to write this vector as a linear superposition of my eigenvectors. Okie dokie. Any final questions with respect to this? Some folks? Can anybody at least tell me that you're following and it's not that we disconnected? Is MC always the same? So, okay, Maya is following and somebody's asking, is MC always the same? What do you mean the same? It's going to change from, so if I'm trying to translate between Spanish and French in this case has a very specific connotation, is these two vectors. These are the two vectors that I'm trying to translate to. If I were to change my original matrix, which my matrix was 2, 1, 1, 2, if I change that, my eigenvectors are going to be different. That means that the change of bases is going to be different too, because I have to translate to a different language. I hope that helps. And thank you both for letting me know. Okay, so let me go back to my things. I'm probably going to talk. Okay, I think we can start with vector calculus in a second, and then we're going to have a break. Let me duplicate these things. I'm not going to go in this in detail at all. I just want to scare you or anti-scare you, if possible. You don't have to learn this by now, but in case you have seen this before, or you will see it at some point in E&M, these are two differential equations. This is a rope differential equation that we were playing with on Monday. And what I want to highlight in here is that what we were trying to do originally was to solve this differential equation for a function phi of x and t. And what we decided to do was to say, let me just solve the normal nodes, the eigenstates of this differential equation first, which for our case, because of the boundary conditions that we have for a rope of length L, the solutions to that differential equation, the eigenstates were these sine functions that were oscillating with this sinusoidal oscillation, that is the cosine of some frequency times time. And then we ended up saying my function phi, I actually think that we call this f, so let me call this f. My function f of x and t, I'm going to approximate it by a linear superposition of these things. So we call this a1 phi1 plus a2, phi2 plus dot, 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 and we found these functions by projection. Make sense? This other equation, this is the Laplace equation in spherical coordinates for a potential that doesn't depend on the azimuthal angle phi. If what I said makes no sense to you, think about it. You will find this differential equation at some point in your education whenever you're seeing electricity and magnetism. Now, this looks like a horrible differential equation. Look at it. It's a partial differential equation in radius and theta with a bunch of signs of theta everywhere. And how the heck are you going to even solve this? Somebody might say, small angle approximation. No, that doesn't work. This thing is not oscillating. This angle goes fully between 0 and pi because this is describing, what is this differential equation describing? For example, it could be describing, I have a metal sphere that has charges on the top, has positive charges on the top, and it has negative charges on the bottom, and it's a conducting sphere everywhere. It's polarized, and then I'm trying to figure out what is the electric field of this monstrosity that is going to be doing crazy things like this. And I'm sitting here like, okay, so from electricity and magnetism, I know that the electric field's potential, B, should solve this differential equation. Well, in this case, I call it F. Imagine that I put this. How do you solve this? How do you find the solution to this problem? You can't. You're not going to be able to just, in most cases, just guess a solution. But if you were to find the normal modes of this differential equation, those solutions in where this thing looks trivial, then, because the Laplace equation is linear, because electricity and magnetism, when you don't have the electrics and things like that, is a linear theory, you can just find those functions and expand your solution in those normal modes of your differential equation, and you just need to find the coefficients that are associated with that expression. That is what I'm writing in here. The details don't matter, but I just want to show you that this concept appears over and over again in physics. These are the normal modes of the Laplace equation in spherical coordinates for something that doesn't depend on the azimuthal angle, in where these things are just expansion in the radial distance r as positive powers and negative powers, and these friends here are called the Legendre polynomials, and they are evaluated in cosine theta. Do you need any of this information now? Of course not. But I just wanted to show you that eventually these will appear in your education. And now the next time that you're listening to this or seeing a book, you're going to remember the rope that we were playing with, and I hope that you're going to feel a bit more comfortable. Okay, that is what I wanted to say on that. Let's talk about vector calculus. Because I realized that I said that I was going to talk about vector calculus, and I did. So it's going to be very brief. Vector calculus. There is just a few things that I want to say. The first one has to do with gradients, and one of the reasons why I told you differential equations were very cool, derivatives were very cool, was because it allows us to optimize things. In the one-dimensional case, you usually have a function f of a single variable, x, and I don't know, that looks like, and then if I'm trying to tell you I have an engineering problem and I'm trying to find the maximum of this function, what do I do? How do I optimize my problem to find the maximum value of this function? Sorry?
Maximum? Taking the gradient?
I don't know what a gradient is. I have a function of one variable.
Derivative.
I take the derivative. Yes? Everybody agrees? I find f prime of x, and I'm trying to find the location. The maximum of this function is going to be a place in where my derivative, my rate of change is going to be zero. Fantastic. Now I say, but what if now I have a function of two variables? I'm going to try my best to draw in 3D. That is not a trivial thing to do. I have some sheet that it is defined here. This is x, y, and this is f of x and y. And I want to apply the same ideas. What do I do? I cannot find the derivative equals 0 because what the derivative with respect to what? So any ideas? Maybe you have encountered this before and you know what to do. And if that is the case, you can speak. What do I do?
You're taking the partial derivative of each variable.
I could take the partial derivative of each term. So I can say, well, consider f with respect to x. I could consider f with respect to y. And then what? Do I say this is 0 and this is 0? But I can imagine myself being in a situation in where the derivative with respect to x is 0, but I'm not at a minimum. I can still climb up y. So what do I do? Let's take a step back. Let's not think in terms of math. Literally think that you're in a mountain, and for some reason I am a very silly person. Maybe I'm an alien not from this planet, and I'm not aware if we have reached the top of the mountain or not. How will you convince me, Pablo? Yes, indeed, we are at the top of the mountain. There is nowhere else to climb. What will you say? Or how will you realize it? Imagine a very smooth mountain. No rocks, like very smooth. You have an idea?
Walk.
Sorry?
Walk and see if you.
You walk and what?
Walk.
I cannot hear you, Ann.
You walk in some random direction, or maybe X and Y.
Okay, I walk. What is, so I am somewhere in the mountain and I can walk randomly around in a neighborhood. What will tell me if I have achieved the maximum of that mountain? What is special about that? Please. Okay, can you check? Get your microphone? Perfect.
Like every surface will either be equal or lower than the surface that you're on.
I like that. That
Like
is that is literally the definition of a maximum. He said, then I'm going to be on top of everything. Yes? But in terms of rates of change, because I want to borrow what I have done from the derivative part, can you think of anything that talks about a rate of change that will help us? I'm just saying the exact same thing. It's like if you're in the highest point, then you have achieved your goal. And I agree. But I want something a bit better than that, that relates to rates of change.
Oh, wherever the rate of change is 0.
But the problem is that I have more than one variable. So the rate of change with respect to which variable? Let me change my question. Imagine that you're not in the maximum, but we're trying to climb the mountain. In which direction you go if you're trying to get further up? How do you decide that the direction you need to walk towards to go to the maximum is, or the summit of the mountain is in a specific direction? How do you know that? Please.
You want to go in the direction of greatest change?
That sounds very reasonable, right? Because if, for example, we're going to improve this drawing. I'm going to literally draw a mountain. Let's see how it goes. Very good. So if you're here, okay, can everybody see the mountain? Let's suppose that we are both here. And we're saying, aha, we want to reach the top. Locally, a good idea will be to look at what is the direction that I can walk through where my function increases the most. See that, for example, going in the opposite direction is a very bad idea. And you could figure out where is the opposite direction very easy. You grab a ball, you put it on the surface and let it go. Wherever the ball goes, just go in the opposite direction, right? You could also walk perpendicular to that in what are called level surfaces. You could walk in this direction. And what will happen if you walk in that direction is that you're keeping your altitude constant. That is exactly what we do not want to do. But at least it's better than walking in the opposite direction and going down the hill. Yes? So you figure out what is the uphill part, what is the direction in where the altitude changes the most, and you follow that. What will happen with this heuristic once you reach the top? What happens at the top? So you keep following this. You're here now, and the blue arrow that doesn't point north, but points to the direction of maximum change keeps telling you to go. Eventually, we arrive here. What happens? Rate is 0. It's flat. So that arrow, that is a gradient, that I'm about to define in a second, will not point in any direction. Literally think it as if you're following a compass to go north because you want to see Santa's workshop, and eventually you arrive exactly at the North Pole of the Earth, what will happen with that compass? It's just going to be doing crazy stuff. It's not going to be able to point anywhere because the North, you're already at the location that you wanted to be. Yes? So that compass is called the gradient. And when we were saying, should I take the derivative with respect to x or the derivative with respect to y? The answer is both. And you call this the gradient of f, and this is a vector. And you take that vector, you follow that vector until eventually you reach the summit, and then you have optimized your function of many variables. There are many other things that we could talk about gradients, and there's some funny shenanigans that happens with functions that are not continuous with respect to their gradients that have discontinuity, and you can get into a lot of all sorts of troubles. We're not going to discuss it. I really want to take a break so that we can stretch, but let me say one more thing with respect to vector calculus, then break, and then we come back to talk about complex numbers and Fourier transforms. Any questions with respect to the gradient? Okie dokie. You have your half of your vector calculus. Second part of the vector calculus. Remember when we were talking about integrals, and I was saying, oh, if you have, why not take it in the c direction? Because my function, thank you for the question, because my function only depends on x and y. The c direction is showing you the height, the value of the surface at a specific x, y location. So c is not a variable that I can take derivatives with respect to. It's basically a response variable with respect to x and y. Okay, good question. So remember that when I had a function f of x, and I was saying, if I want to calculate the area under the curve, or as all of you are experts, that is not the important part. The important part has to do with rates of calculating the effect of many things put together. If I want to evaluate that between a and b, I want to add all of these things up and calculate this area, we figure out that the integral of f of x dx between a and b was equal to a higher up function, big F, evaluated at the edges. And this function f had the property that if I were to take the derivative of this function, I will get my tiny function f of x. So the problem of finding areas under curves translates to finding antiderivatives and then evaluating that on the edges. Make sense? Here is a couple of cool things from vector calculus. Suppose that the first one is the divergence theorem. And the divergence theorem is telling you that the integral, that if I want to, exactly, that if I want to integrate, okay, that if I want to integrate a function f that is a vector function, so that means if I have a surface, like a blob, a potato, and this thing is a vector field, that means that it's a bunch of arrows going in different directions. If I want to know how much flux is coming out of this surface by this integral, by this function, that is this integral that I'm creating in here, I'm realizing that I don't have enough time to go on this in detail. So I really will just mention it, and I'm going to create the videos later that are going to help explain these things. But basically, this is telling you, you're trying to find the flux of this vector function through this boundary that is equivalent to doing the volume integral of the divergence of this vector field over the entire volume inside. And here are two things that I want to say about these things, and that is the final stuff. I'm not going to talk about the curl theorem at all. The first thing that I want to say is, see that the same thing is happening. I'm able to put this inside. Let me write it in here. Inside. This is a parallel that I want you to see. Outside. And these two things are outside. Basically, this is telling you the accumulation effect of something, in this case is the divergence of my vector field f, inside a surface is equivalent to the accumulation effect on the edge of that surface of something else that has to do with antiderivatives. because this divergent operator in here that I haven't defined, but maybe you have seen it at some point, is something that takes derivatives of vector fields. That is the exact same thing that was happening in the one-dimensional equivalent of calculus. In here, I'm saying the accumulation of an inside effect of my function, the area under this thing, is something that I can explain by just looking at the edges of this region and evaluating an antiderivative of my function on that region. So if this resonated with you, fantastic. If it didn't, don't worry. It's recorded forever and ever, and whenever you feel you face something regarding the divergence theorem, you can come back in here. But I wanted to make the connection with the regular integration on its own. The final thing that I say, I promise, and then I leave you to go. The intuition behind this divergence theorem, I usually like to think it in terms of a bathtub. Imagine that you have a bathtub or a fountain of water, and you have a magic loop, like, I don't know, Wonder Woman's magic loop. You put this loop in here, you have a bunch of water, and the water is swishing back and forth. Are you all following me with this crazy analogy? Okay, and the water is swishing back and forth, and this magic lasso is able to tell you how much water is entering and is leaving at the same time. So for example, if there is some water moving in this direction, maybe some water enter, and there is some water that is leaving the lasso, and then in here, I don't know, maybe I have a swirl or something like that. Hello, Josh. Now, I want your conclusion on this. What do you think means if I were to tell you, friends, for a while, I have been monitoring the amount of water that enters the lasso and the amount of water that leaves the lasso. And there is more water entering the lasso than there is water leaving the lasso. What is your conclusion in this physical situation? Any ideas? Think about it. Is the water...
There is a hole into the surface.
Sorry, go ahead.
There is a hole into the surface, in a closed surface.
I really think that you have the right idea, but I cannot hear you very well. Can you repeat one last time?
I will write it.
Okay, write it. While we wait, if anybody else has any ideas, you can say them. The water seems to be entering, but the water is not leaving. How is that possible? Is it magic?
And this lasso, this means it's like 2D.
It's a 2D, yeah, but I have a fountain, so it's a 3D object. It exists in real life, and I will build it the next time that I make these things. But you're seeing that more water enters the lasso than leaves. Somebody says there is a hole in the surface. It's being absorbed. I like those things. What if then you take the water out and you see that in here, there was a sink and the water was just, some of the water was going through a pipe and was leaving. That is your conclusion. And that's the conclusion that I want you to have on this. If you have a surface and you have a flux that is entering the surface and some part of it is leaving and the net addition doesn't add up, that means that there is a sink. That means that if you want to know how much water is net entering or leaving, you have two options. Either you use the magic lasso and you count how much water enters and leaves, or you count the number of sinks inside the lasso, and that will give you information on how much total water enters plus leaves this thing. You could also have sources. So this is going to be a fight between a certain number of sinks that are absorbing the water and a certain number of fountains inside the pool that are creating water, because you could have the opposite effect as well. That is what this theorem is telling you. This theorem is telling you the amount of water that comes in. Either you calculate it on the surface, and that tells you that, or you count the amount of sources or sinks, add them all up together, and that is going to tell you net effect of the amount of water, in this case, that is entering only. You're going to use this in electricity and magnetism because the sources and sinks of electric fields are charges. So if you have a region in where you have total positive net charge, the electric field looks like a spiky thing that is leaving that region. Electric field is being generated by the charge. If you have negative charge, the total thing is absorbed. And that is called Gauss' theorem. And I have no idea why I decided that this was important for you to know, because we're not going to be talking about electricity. But I wanted you to have the intuition. There is something similar with something that is called the curl theorem that tells you about rotations instead of spikiness, but we're definitely not talking about that because otherwise I'm not going to have time to do my thing with the quattro. So I'm going to stop sharing. In my clock is 2:23. We're going to come back at 2:28. Go to the restroom, stretch. I'm going to stretch here in the class, and we'll be back in a second. Friends, sorry for interrupting, but we have to come back to the class. But I'm very glad that I'm already seeing people here that are making lifetime friends. Okay, let me share screen again. So I have 30 minutes to talk about complex numbers, to talk about Fourier transform, and to play with the guitar, with the quattro. We can do this. I believe in us. Okay, so complex numbers. We have a online guide in the Python resource thing that is still on the making, but it's already public. You can check it out. In that one, we define a bit what complex numbers are and how you can use them for differential equations. The main things that I want to say is I will say a couple of things about complex numbers. The first thing is, why will we need complex numbers at all? Well, the first situation in where something like that arises is if you try to solve complex. If you try to solve an equation, normal equation like this, in where within the real numbers, you don't have anything that you can plug in this equation that will give you a satisfying answer. You can always just say, well, this has no solution. Yeah, but where is the fun on that? So you expand the notions of what normal numbers means to include this new number that is called I, which you define as the square root of -1. And you say, yep, let's go for it. Now, some people have said, are complex number real? Nothing is real, so no, I guess. Numbers are not real either. You can say I have 3 sheep. Yeah, but maybe, I don't know, one of your sheep is missing a leg, so you don't actually have 3 sheep. You will have 2-point-something sheep. So at the end of the day, many of these concepts and mathematical constructs, we do them, in my opinion, on 2 motivations. Either they are useful for describing things on reality. Complex numbers are certainly extremely useful to describe many things in reality, or they're just fun. It's fun to play with. And that is what mathematicians and other people that really like math tend to do. I count myself among those. So complex numbers are extremely fun. I'm going to show you some cool animations, but I want you to think of the complex plane. If you have never thought of this before, literally think of a complex number C as a number that has a real number A plus I times another real number B, and these are coordinates in the same way as we have been describing with vectors. So this complex number C will look like an arrow. This is a complex plane, so this is the real, and this is the imaginary axis. And this complex number C has a real part that looks just like an X component, A, and has an imaginary part that looks like a Y component, B. And that's it. You know the complex plane. Things start getting very interesting when you start creating functions of complex numbers. in particular, one of the functions that there's two functions that I want to mention that are very important. The first one is e to the I, let's say theta. This function as a function of theta, I imagine you have seen it before. I'm not going to take any more questions to streamline the discussion, but it's in your playground, is to prove or convince yourself that indeed this function is equal to cosine of theta plus I times sine of theta. Which is a pretty cool thing to do, because then if you were to represent this in the complex plane, this number c, you can write it as some distance r times an angle, the angle theta. How do you write that angle? Well, you write this e to the I theta. And this is the polar representation of complex numbers, in where instead of giving me a x and a y coordinate, as we discussed in one of the, I think it was last lecture or the lecture before, on representations of vectors, I can use two different representations for complex numbers, and that is completely valid. So this is one of those functions that are important. This is the thing that connects wavy stuff with exponential stuff. They're basically the same function. Exponentials are sines and cosines in disguise, or you can say it the other way around. Sines and cosines are just exponentials in disguise. And that's why the two differential equations that I committed you to memory, if you remember, f prime is equal to lambda f, and f prime prime is equal to minus lambda squared f. You can go back and forth with exponentials and sines and cosines, depending on the sign of your frequency, at least on the second one. So that's why these two things are related. That is the first thing that I want to say. The second thing that I want to say, there is a very special function in complex analysis, which is 1 over c. This function is extremely special. And the reason why this function is special is because the antiderivative of this function, anybody knows what is the integral of 1 over x? Logarithm. So what will be the integral of 1 over c?
1 over z.
Logarithm. Don't think. So then the antiderivative of this is equal to log of c. And here's the problem, because log of c, now I can be talking about complex numbers, and remember that the logarithm is kind of the anti-function for the exponential. So look how the exponential looks on the complex plane. It looks like this e to the I theta. So the logarithm or the anti-exponential of this is going to give me the value of theta. But e to the I theta is a multi-valued function, because theta, if theta is equal to 2 pi, this basically gave one rotation and is on the same place. So the logarithm is going to have some shenanigans happening to it because of this multi-valued stuff. I'm going to show you that in a second, but that is what the fact that the log has this problem with the exponential, and the fact that the log is the antiderivative of 1 over c makes 1 over c a function in where if you start doing counter integrals, basically you try to write an integral of this function around a closed loop in the complex plane, you're going to accumulate a certain amount of area or phase, if you want to think it that way. That is called the residue theorem. Is that basically if you were to integrate this function f of c dc in, I'm making, okay, let me put this in here. You make a counter integral of this thing around 0 in any counter that encloses 0, in where this function has a pole or an explosion, you're going to end up finding that this is equal to 2 pi I, where any other complex function that doesn't have this type of properties will give you 0. This is very similar. I'm almost done with you. This is the thing that I want you to think in your head. This is equivalent as if we were on the mountain and we decide to walk around on a circle, and we end up arriving at a different height as we were original. That makes no sense. That shouldn't happen. That happens for complex functions, and I'm going to show you a plot in a second, the functions that have 1 over c. And that is a property that we end up using to evaluate many things, including real integrals whenever we don't know how to Okay, sorry, please, go ahead.
I was just going to ask, is it like natural log?
Yes, yes, sorry, I write log as natural log, but yes, is the log regarding the exponential. Yes, let me put it in here. Log is equal to log. Yeah. Okay, because I only had 10 minutes to talk about complex numbers. If you are lost, that's okay. This is just to give you some intuition for later and to give me the excuse of showing you some cool plots that are already part of the GitHub visualization folder. So this was generated by ChatGPT. This is the function 1/c that I was talking about. Now, the problem with complex functions is that, well, there are many problems, many interesting things. You see that I have the real axis and the imaginary axis, but the output of a complex function is a complex number. If you want to think that in terms of vectors, the output of this function is another vector. So how do you visualize that? F of c is not a real number, it's a complex number. So one thing that people usually do, you plot it in such a way that the c value in here, the height, is the magnitude of my function. Remember that we are dealing with 1/c. So indeed, as you go to 0, this thing just blows up. And the color has to do with the phase, with the angle theta of the complex number that we're talking about. Remember that I was saying that these things are basically like vectors. This is the function that blows up if you are just looking at the magnitude, but this, this is continuity in here is what creates this very interesting flavor for the function that ends up being useful for complex analysis. In the visualization, I also included the opposite, in where instead of showing as the height, the magnitude, I show in the height that angle. And this is what I was talking about, that if you start walking in a circle around the surface, once you come back to the same place that you started from, you are 2 pi I difference from your original starting point and your final starting point. And that is what ends up powering a lot of the complex analysis that people do in afterwards. Will be important later for some of the things that we will discuss in quantum mechanics. But now at least you have a visual representation for this. Okay, let me go back to successfully completed complex numbers in 10 minutes. Let's now talk about Fourier transforms. And then with that, we're going to play with the guitar. We're going to be done. Fourier transforms. The idea of a Fourier transform is the exact same thing that we were saying before when we had our rope in some initial state. And I say this function x of f of x and t, I want to approximate this as the linear superposition of my normal modes dot dot dot. Here's the thing that I want to convey to you. This object, if I want to give you the information on where the rope is right now, at the beginning of time, I can give you two pieces of information. I can either give you the plot of f of x at this particular time. Yes, that will tell you how the function is looking right now. Or I could just give you these numbers, a1, a2, a3. If I give you a list, a1, a2, a3, dot, 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 of all these numbers, you know how the function looks like, right? Folks are following me? Some people? Josh, are you following me? So I could talk about the object as f being the list of the value of the function at every grid point. This is f of x1, f of x2, f of x3, dot, dot, dot. Or I could talk in terms of f as the list of coefficients, a1, a2, a3, dot, dot, dot. I'm talking about the same f, and I have the same information to reconstruct the function if I need to. Does this rings a bell to any of the things that we have discussed today in class? These two are the same f, but I'm writing them in a different way. Does this rings a bell to anything that we have done? Please say it on the microphone. Somebody saying change of basis. So I'm talking about the same book. I just have the book written here. The vectors, yes, of course, these are vectors. But the important part is the change of basis. This is a book in Spanish, and this is the same book in French. And just to distinguish between the two, I'm going to put a hat in here just to remind me that this is the same object, but I'm just writing it in a different basis. One is a basis of the value of the function at each location x, and in another basis is a basis of coefficients that I need to multiply by these normal modes in order to recover my function. It's the same object, just written different. That is what a Fourier transform is. Whenever you go to a situation in where you don't have a finite interval, but rather your function lives on x going from minus infinity to infinity, you're going to need a lot of these coefficients. You're not going to be able to just get a handful, but you get a Fourier transform, which is telling you your function f of x. You can write it as a linear superposition. Let me put this in here. This a1, a2, blah, blah, blah. I'm going to call it f hat of, let's put it omega. Omega are the different frequencies. Remember that these normal modes, I had one that was oscillating very slowly, one that was a bit faster, one that was even faster, and so forth. So that is this frequency omega. And what are my sinusoidal functions? Well, in this case, because we just said that exponentials and sines and cosines look the same, I'm just going to stick e to the I omega x in here. That is just a sine. That is, think of this as this rope that is moving in this way, and I need to make a superposition of all of these things. Well, I just make an integral over all possible values of my frequencies omega. We're going to touch on Fourier transforms in more details later, but I want you to think whenever you see this object is the exact same thing that we did in here. You're just changing the basis that you're using to expand your functions. Instead of telling me the value of the function at every grid point, you're telling me how to reconstruct these objects as a linear superposition of oscillating stuff. Okay, today's class has been very dense in terms of mathematical concepts, but now we're going to have fun with the guitar. Before we go in that direction, any questions, clarification questions that are important to say for now and for the generations to come? Remember that if the microphone is on, okay. Let's now play with the guitar. We have 15 more minutes. I'm going to need a volunteer to record this. Can you come, Lauren? Thank you. I'm going to need a second volunteer to record voice and then the guitar. Who wants to help me? Who has not helped me already? Lauren, here you go. Just record the entire thing. And you have creativity freedom on where you want to stand and how you want to record. But you can start already. No, you treat yourself as a camera crew first and do it in an artistic way. I'm going to stay here and I'm going to bring somebody to. Okay, who wants to help me that haven't helped me before? And do you want to help me?
Yeah, how do you want me to do it?
Come here and bring the microphone. Okay, are you recording? Thank you. Okay, so let me share. How are we going to do this? Come here. So the first thing that we're going to do, let me share screen. We're going to come in here. We're going to record some. So, are you ready? Comes on so that the Zoom folks can see you as well. Okay, so I want you to record something in audio for, let's say, 10 seconds. Say something.
Hi, everyone. My name is Anne.
Mm-hmm.
I'm Pablo's student. Good to see you guys. Is that 10 seconds already?
That is 10 seconds already. Good job. I think I have done to you the hardest thing that anybody can ask somebody, which is like, say something interesting. But you managed, so very well. So I'm going to export this as audio. Perfect. Let's say here, and record. Okay. So now, with the help of ChatGPT, I have written this code that is going to make a Fourier transform of answer recording. We're going to analyze it. Let's run it. Okay. And this is your voice.
Yeah.
That is a time series of your voice. And the thing in red is basically the coefficients that we were talking about. Is if you wanted to reconstruct exactly what you just said as a linear superposition of sines and cosines, that is a recipe that you need to follow to be able to do it. And that's what we're going to do now. The next code is going to grab these Fourier modes, and we're going to keep the first 50, the first 500, the first 5,000, and so forth, and try to reconstruct your voice. It's the exact same thing that we were doing with the rope. Whenever we were only using one normal mode, two normal modes, three normal modes, the more we do, the more fidelity or reconstruction is going to. Are you ready? Let's see how this looks. Okay, we're going to hear them. I don't know if Zoom folks, you're going to be able to hear this. I'm going to upload them later to the folder. I hope that you are, but at least I think it's going to at least show us in the plots. Let's see, still processing.
I have a question.
Please tell me.
You show the plan. Wait. Are these the number of like modes or number of functions that we have? Or
This is the frequency. So that is showing the frequency of oscillation. Things that are very close to zero are moving super slowly, and things that are very high are moving very fast. And this is in hertz. So human voice is around hundreds of hertz. Actually, if you play the A note in a violin, that probably is very far away. Lauren can tell me,
yes.
but that will oscillate at 440 times per second. That will be this line. So I could literally record myself singing that and see how off I am just by looking at the Fourier transform. Okay, so let's see at your reconstruction. This is what we will obtain if you only use 50 modes. This is what happens if you use 500. This is what happens if you use 5,000. This is what happens if you use 50,000. And if you use
a lot,
you actually reconstruct the thing. Let's see how it sounds. So let's go with 500. Sounds super eerie.
Yeah.
I don't understand anything.
It's like a cave sound.
It's like a cave sound. Let's go for the next one. 5,000. Can you hear yourself?
Yes.
I will upload this so you can hear it later in detail. But you can hear your voice. It's just not as good. But if we go to 500,000.
Hi everyone, my name is Anne. I'm a student.
Isn't that cool?
Good to see you guys.
This is literally multiplying these numbers by these oscillations of different frequencies, and that creates this sound. That's very cool. Now we have one more thing to do. Are you?
Wait, one more question.
Please go ahead.
What is the mode in the graph that you showed, like the previous graph? What are the modes? How many?
Well, this thing discretizes frequency, so I will have to look at the specific values. But you have a frequency at 697.25, blah blah blah. You have one. The next one is 707. It creates an approximation because the frequency will also be a continuous thing that no way the computer cannot do. Does that make sense? Okay. Now the next thing that we're going to do, and that is the final thing in here. Okay. Let's now erase this, and we're going to play one note from my cuatro. Can you help me hit record? And I will play it close to my microphone.
Close enough?
Yeah, that is good. You need to help me hit and record in there with the mouse.
Wait, where?
In there, and then you're going to don't do it yet, and then you're going to hit stop after. Start, go. Okay, thank you, Anne. You can go back to the table, and we're going to analyze this one now. You can stand here too, of course. So let's export it. That was a D note, hopefully, yes? Or expert E. close enough. Let's put D more or less. Okay. So my question to all of you, before we analyze this, how should the Fourier transform of this look like? Any ideas? This is how Ant's Fourier transform was looking. What do you think is going to happen? And could you take this there so that we can hear?
My thought is that it should show just kind of one specific frequency.
Just so one, which frequency?
I'm not a music person.
Whatever is that note, right?
Yeah.
Which is, as our experts have told us, it's not exactly the note that we should have. It's going to be around 440. No, because it's a D note. So that is around 300 and so. But yes, close enough. It's going to be close to that, but not exactly. And I want you to tell, and it's not because the thing is not tuned. It's because of other reasons. Let's look at it, and then I want to hear your reasoning on why. This is how it looks. This is my peak. Around 300 and something. If anybody can Google what is the exact frequency of a D note, so we know how off tune that thing is. But there is other spikes. Well, first of all, the thing is very spiky. It looks very different than the spectrum of a much more rich audio, which was Ant's and mine conversation. So this is much simpler. It's just a bunch of spikes. Why is there more than one spike? Anybody figure out the frequency of D? 294. So indeed, we are up. But we were close. But why different peaks? Any ideas? Those are harmonics. And this is extremely important. Those things are the things that make the cuatro sound like a cuatro. If it was a single frequency, it will sound like a very rudimentary Atari music. Like awful. That is awful to listen to because it's a pure frequency. Your ear doesn't have any flavor to relate to. So a D note in the cuatro will sound very differently than a D note in the violin or a D note in the piano. They will have all the same biggest spike in the same frequency, but then all of these harmonics or extra parts are going to make it more interesting. Let's hear it. If I were to reconstruct this, this is a signal reconstructed with 50, with 500, and with 5,000. Let's see how they sound. That is close to a pure note. If I go a bit up, that sounds a bit more interesting. And if I go to 50,000, that starts sounding more close to that. That is how these things work. So in terms of formal Fourier transform, let me stop sharing my screen now. All of these codes are available in the GitHub, so you can go and play with your own recordings and look at your Fourier transform. In terms of formal Fourier transforms, this is telling you that if you have a perfect sinusoid, the Fourier transform of that, of a perfect sine of a given frequency, should be infinity at that frequency and 0 everywhere else, because you only need that as a recipe to make the actual signal that you're after. That's why the Fourier transform of sine is delta, for those of you who have seen delta functions before. I will release a video on that and I will touch on those details later. Okay, that is the end. Thank you, Lauren. You can stop recording now. That was a good exercise. Thank you. So that is the end of today's lecture. We have 4 more minutes before I say some closing remarks. Any questions or any comments? Any follow-ups?
I have a question about the playground.
Tell me, Josh.
I'm sorry if I missed this because I came in late, but
No problem.
For the differential equation that you want us to solve using a Fourier transform, do you want us to like motivate like the linearity of doing Fourier transform? I remember doing that a lot when I was learning this in ODE. Or can we just move forward assuming that we know that the transformation is linear?
I am never going to grade anything, so you can do whatever you want. You already know that it's linear, and I actually wanted to touch on details on how to solve differential equations using Fourier transforms, and I didn't have the time. So if you know how to do it, go for it, and you can then put it in the forum, and that can help to other people to discuss things. The same for integrating using the residue theorem. Everybody that is watching, give it a try, and we can discuss it later on more details, but I just didn't have time to go into details on how you will get this to work. In this case, you're going to do a Fourier transform of this differential equation. Derivatives are going to act as just multiplying by the frequency omega or the frequency k, however you want to call it. And then the problem is going to end up just being an integration problem, which, as we have discussed before, integration is step 2 in the ladder of problems. You're going from a problem level 3 to a problem level 2, so that is some gain. So, later, my recommendation: do whatever you want, try it, and submit something that we can look at it. And it will make me very happy if you solve the problem numerically by doing the Runge-Kutta integration, and then solve it through Fourier transforms, also numerically to integration, but to see if both solutions kind of agree. This is also related to the GitHub guide on complex numbers. It has an idea of how to solve differential equations using Fourier transforms, so that should be useful as well. But thank you, Josh. Good comment. Any more questions or comments? Okay. Here I have something in the chat. Why will one use the Fourier transform in everyday life? Well, you're connecting through your phone, so that is already doing that. Whenever you send signals, or at least the way that it was used to, I don't know if new technology is different, usually audio signals are decomposed into Fourier, and what gets sent between places is those coefficients. I actually think that the MP3 encoding or file type is exploiting Fourier transform things to be able to efficiently save audio in a way that it takes less space. So you're using that every day in your life if you do anything with files. You wanted to say something? No? Okay. Okie dokie. Officially, that concludes our lecture today. It was an absolute pleasure to have you all here. Thank you. I will see you Monday for our first lecture on classical mechanics. I have no idea what we'll discuss. I will figure that out in the next couple of days, but I will see you then there, and enjoy the rest of your week. Thank you, friends.